Welcome to today's Explainer. We're about to unlock a piece of tech that sits right at the intersection of cutting-edge artificial intelligence and our everyday lives. We're looking at the future of how we interact with our smart devices, and specifically, how we actually get their attention in the first place.
Okay, let's dive into this. Have you ever been, just a little frustrated by the fact that you're stuck saying, "Hey Siri," "Okay Google," or "Alexa," day in and day out? Like, why can't you just rename your voice assistant to computer, like in Star Trek, or maybe your favorite fictional character? It feels like it should be a simple software update, right? Well, behind the scenes, allowing users to define their own wake words is actually an incredibly complex engineering nightmare.
So, here's our roadmap for today's Explainer. First, the custom wake word problem. Then we'll cover the three pillars of the solution: dual stage matching, multi-modal enrollment, and continual adaptation. And finally, why this matters.
Let's start with Section 1, the custom wake word problem.
To really appreciate the solution we're going to talk about, we first need to understand why our current devices are so rigid. Standard voice assistants use what's called predefined keyword spotting. Tech giants spend literal millions of dollars and train their AI on thousands of hours of audio just to perfectly recognize a single fixed phrase. It's super effective, but completely inflexible. On the flip side, we have user-defined keyword spotting. Now, this promises ultimate flexibility from just a tiny amount of data, but historically, it struggles terribly. It gets confused by different accents, and it constantly trips up over words that just sound similar.
But there's a new academic paper that is an absolute game changer here. The research is titled Effective User-Defined Keyword Spotting with Dual Stage Matching, Multimodal Enrollment, and Continual Adaptation. This brilliant work was done by researchers ZQI, Han Cheng, Shi Mu, Sinhua Li, Youngjin Zhou, and Shugong Zhu, spanning across Shanghai University, NYU, and Xi'an Jiatong Liverpool University. The authors hit the nail on the head right in their abstract. They state that user-defined keyword spotting is absolutely crucial for personalized voice interaction. But they call out three massive roadblocks: insufficient discriminability, which basically means the AI gets confused easily; performance inconsistency, meaning it really struggles with different people's voices; and high data cost, meaning it usually takes way too much computing power to train.
And this brilliantly illustrates the researchers' answer to those roadblocks, the DMA-KWS framework. It creates this flexible, continuous loop. A user can type in a custom wake word using just text, or they can give a quick little voice sample. The system then processes that through a highly efficient engine that continually adapts to the user's specific voice. So let's break down exactly how this engine works under the hood.
That brings us to Pillar 1, dual stage matching. This is how the system solves the problem of getting easily confused by similar-sounding words. These spectrograms, which are essentially visual representations of sound, show us exactly what the AI hears. The system has to differentiate between your wake word and literally everything else you say. Notice the top two, himself versus herself. These are what we call hard negatives, because to a machine, their acoustic footprints look almost identical. Traditional custom systems fail here constantly. An easy negative, like the word sometimes at the bottom, looks completely different and is super easy to ignore.
So, to catch those tricky hard negatives without burning through your device's battery, DMA-KWS uses a very clever two-step process. Think of step 1, the CTC decoding, like sweeping a pitch-black room with a really wide flashlight. It does a fast, streaming search just looking for the general phonemes or sounds of your wake word. When it thinks it found something, boom, it triggers step 2. This is the QBT phoneme matcher, which acts like a magnifying glass. It takes a highly detailed, fine-grained look at that specific snippet of audio to ensure you actually said himself and not herself.
Moving right along to Pillar 2, multimodal enrollment.
Now, this is all about personalization and dealing with the beautiful but incredibly complex variations in human accents. With text-only enrollment, you just type in your new wake word, let's say, "Hey great," and the system uses phonetic spelling to listen for it from anyone. That's fine for general use. But with speaker-dependent enrollment, the system uses text plus audio. You type the word and you say it out loud once. This is a massive leap in complexity for the AI, but it completely changes the game for accuracy.
The secret sauce making that possible is the multi-modal alignment module, or MAM. The MAM fuses the text you typed with the specific acoustic quirks of your actual voice. Whether you have a deep Southern drawl, a heavy Scottish brogue, or a quick New York clip, The MAM captures exactly how you pronounce those letters. It anchors the AI to your specific voice, which pretty much eliminates the chances of someone else accidentally triggering your device.
Next up, Pillar 3, continual adaptation.
See, it's one thing for a machine to learn a wake word in a perfectly quiet room. It's another entirely to recognize it when the TV is blaring, the dog is barking, and you've got a bad cold. DMA-KWS solves this by constantly learning, but it does so incredibly efficiently. In Step 1, the system actually generates its own synthetic training data. It uses text-to-speech to artificially create examples of your wake word in different simulated environments. Then in Step 2, as you use the device in real life, it applies lightweight updates using something called a LoRa adapter. Instead of retraining the whole massive AI model from scratch, which takes forever, it just tweaks a tiny, highly specific part of the network's memory.
Finally, Section 5, why this matters. Let's talk real-world impact.
We've talked about dual-stage matching, multimodal fusion, synthetic adaptation. But what does that actually mean for the smart speakers sitting on your kitchen counter? Well, on the incredibly difficult Libre-Phrase hard subset, which is essentially a torture test for AI using highly confusable, similar-sounding words, the previous state-of-the-art method had an equal error rate of 8.47%. DMA-KWS drops that error rate down to a staggering 6.13%, while pushing overall accuracy up to nearly 98%. It is definitively mathematically better at distinguishing your specific wake word from a sea of background noise.
But honestly, the craziest part is how they achieve this without requiring a literal supercomputer. When the system updates and adapts to your voice on the fly, it only updates 187,000 parameters. In the world of AI, where models routinely have hundreds of millions or even billions of parameters, 187K is practically nothing. This means this advanced, highly accurate, continually learning AI can easily run on the cheap, low-power microchips found in everyday smart home devices.
To sum this all up, this research isn't just some tiny incremental step. It's a massive paradigm shift. DMA-KWS achieves state-of-the-art accuracy on the hardest, most confusable words out there. It natively handles your specific accent rather than forcing you to speak perfectly like a robot. It radically lowers the computing cost by using tiny, continuous updates. And ultimately, it paves the way for a future where smart devices are truly personalized to you, right out of the box.
We are finally moving past the era of being locked into predefined corporate wake words. The engineering barriers, the high data costs, the accent struggles, the easily confused words, they're all being dismantled by brilliant architectures like DMA-KW. So, I'm going to leave you with this question to think about. Now that the technology is finally making it possible, what will your custom wake word be?